My name is Adam Manzanares, and I'm part of the global open ecosystem team at Samsung. And Anisa is going to be presenting with me as well, and I'll give a high-level introduction of some work that we do on this team. And the title of our talk is CXL Ecosystem Innovation Leveraging QEMU-Based Emulation. And our work is very developer-focused, and so I think we have a live demo included. And so the main point of what we want to deliver to everyone here is that there are options for those that don't have CXL hardware, and they're starting to try to plan how they may integrate it into their software stacks and what it may look like to use CXL. I think it's a great way for people to start getting involved, and I'll talk a little bit about Samsung's use of it. All right, so first background, if this audience here has not been using QEMU before. So what it is it's an open source tool, so you can Google it and find it, and it runs on Windows and Linux and maybe other OSs, but the key part of what QEMU does is that it provides emulation and virtualization. And for this work, when we're talking about CXL, what do we really care about is that it can emulate peripherals. And you can have full system emulation, right, is that you could, on an x86 machine, you could be running ARM. You can also do user mode emulation. And the last thing that it also provides that's very useful is that it can use existing hypervisor and then have like full speed emulation of hosts on a system, right? So you can have like rapid prototyping between the changes you make in your emulated hardware and then your kernel driver support at the same time. So QEMU has been a pretty handy tool for us in many ways, and I'll go through that in the next slide. So why is QEMU useful, and why would I want to talk about this to this larger group and evangelize this in many communities, is that I've seen it used in practice at multiple companies, and what it has been very useful for is we can rapidly prototype end-to-end software for new hardware features, right? So we can actually prototype them inside of QEMU, get the host software stack running, and yeah, we don't initially look for performance immediately, but we do look at how end-to-end applications can integrate these new hardware features. And so what I see this is, many people will talk about hardware, software, co-development, and this is the era of designing hardware and software, but we've been doing it for a while, and we have known successes. And it doesn't always work out in terms of the technology adoption, but in the end, that's not the key. The key goal, of course, would be that it gets adopted, but the fact that we can prove it out before is actually the most valuable part in my mind. And some examples that we had is that we had ZNS support, data placement technology for NVMe storage done in QEMU. We've also done FTP inside of QEMU. And then lastly, CXL. And then we create the host software leveraging these features. And so we're a software development team, and we look at Linux kernel drivers and applications. Our main goal is to make a blueprint of how to use these technologies. And we can move fast. We can move faster than hardware comes out. Right? You have the hardware prototyping. Eventually, you have to have SoCs come out. You need firmwares. There's this very complex set of steps that has to happen to have a hardware. But we can already kind of make a proving ground of how this may look. And Samsung has had successes leveraging QEMU in NVMe and CXL support. And how do we make success here is that we work closely with the device testing teams, right? So they help get testing frameworks set up before the final hardware is available, and so that we test all the features and we know what to do. So we work very closely with these large testing teams that start building their frameworks very early on, leveraging QEMU, and it allows us to have this quick adoption of hardware. And one of the things I like to bring up, especially here at a venue like SDC, as we talked earlier, our goal is to bring other people into this ecosystem. The more people that get exposed to how to use these technologies, say CXL, new NVMe features, the better off I think it is for everyone that we can prove these ideas out. And so part of this is all done in open ecosystems, and it's available for you to use. And my last slide here is that, so now why CXL devices, right? And I think it's interesting to think about it from this community, from the storage developer community. And so one of the things that we've noticed, and it was even mentioned earlier, I think, in Andy's talk, is that CXL hardware availability is limited. And that's not a restraint that we face personally. You know, Samsung, we're developing hardware, so this is not an issue that we face internally. But in order to move faster, it's nice to move without having that hardware dependency. And so we like to do it just to move fast for ourselves and then see what other people do with the technology as well. And, you know, we're going to reproduce the success cases we've had with NVMe. We've had success cases related to NVMe around this. And so, yeah, we want to just kind of copy that model because CXL has a device driver. It's a PCI device from the QEMU perspective. And so it's very similar and can benefit from the same. So in the end, where are we seeing the major benefits from this emulation? Operating systems development, that has been an area where we move really, really rapidly. And so driver development, application prototyping moves forward with this emulation. And then CXL, and this is what Anisa will get into coming up, has this concept of building memory fabrics. And this is, you know, I think it's been talked about in NVMe, like you look at NVMe over fabrics. And so CXL has a notion of building fabrics as well. And there's some complication about switch support being involved, and there's more components that are involved in the CXL hierarchy. And so now managing these systems is actually, you can start prototyping and looking at this and what the end-to-end software looks like. So even what a BMC might look like for managing devices, and then how do you actually compose these fabrics? So, you know, then I'll hand it off to Anisa with the details.
Okay. Yeah, thanks, Adam. Okay. So what can you currently emulate through QEMU? But first I want to make a quick disclaimer that not all of the features I'm going to talk about are in upstream QEMU, especially some of the newer ones. The newest features are carried out of tree by the core maintainer of this module, Jonathan Cameron. So to access some of them, you may need to use a branch published to his personal GitLab. But to answer the question, right now QEMU supports emulating CXL memory devices and CXL switches. And within CXL memory devices, there are different subtypes. So there are volatile or PMEM CXL-enabled devices, and also dynamic capacity devices, and more recently, some support for multi-headed single logical devices, or MHSLD, has been added. But for the purpose of this presentation, I'll be focusing on dynamic capacity devices specifically. So in addition to what kind of devices you can emulate, there's also the question of how to talk to those devices, and in QEMU there is support for both in-band and sideband communication. And to make that bit clearer, I'm going to go over this diagram for a more concrete example of a topology that you can emulate. This diagram shows a pretty simple topology with a CXL switch that has 3 downstream ports, each with an endpoint device attached. And we also have a BMC, or baseboard management controller, which is just like a specialized controller that allows you to remotely monitor and manage your server components. So in this diagram, we can see that the host and the BMC talk to the switch through 2 separate endpoints. And this separation is defined in the spec by something called a CCI, which stands for Component Command Interface. And the purpose of a CCI is to define which commands the device can understand and how the device is able to receive them. So in the example here, the switch implements 2 CCIs, meaning there's 2 ways to talk to it. And one CCI defines what commands it can receive through its MCTP endpoint, which the BMC is connected to, for sideband communication, and the other one defines what commands it can receive through its other endpoint, which the host goes through for in-band communication. And so earlier I mentioned that the focus of this presentation will be on one of the newest features supported in QEMU, dynamic capacity devices. Now that we have like a better idea of how everything fits together, I'll define what it is exactly and introduce the related concept of fabric management. So dynamic capacity devices are a subset of CXL memory devices that specifically allow you to add or release system memory without resetting the device through a process of adding or releasing extents. And this process is facilitated by the Fabric Manager, or FM, and its main role is to dynamically configure the system's operational state using the FM API. And note that the FM is a logical process, not a hardware component. So you can run it on the host, on the BMC, like in our example, or on a switch, or even as a state machine on the device itself. And I'll go over how the FM host and device interact in more detail in the next slide. But just to quickly recap this slide before we move on. Right now in QEMU, you can emulate CXL memory devices and CXL switches, and both in-band and sideband communication. Okay. So as promised, I'll talk in more detail about how the Fabric Manager, host, and device interact. So specifically, I'll explain how memory is dynamically allocated. And this begins with the Fabric Manager, which initiates the process by sending the FM API add command to the device, telling it to make some extents available to the host. Then the device will process this command and record this information in an event log and trigger an interrupt to the host. The host gets notified, looks at the event log, decides which extents to accept or ignore, and then it will send its response back to the device, and the device finally physically allocates memory for that host. So in the previous slide, I said that we can emulate the device in QEMU, and the host behavior is part of the CXL driver, but that still leaves the Fabric Manager, and we need a way to send that first FM API add command to jumpstart this whole process. And that leads me to my next slide. This is where we see the need for libcxlmi, which stands for CXL Management Interface Library. This user space library allows you to send any command to any CXL device. And so for those of you familiar with libnvme, this is the equivalent for CXL devices. libnvme and NVMe CLI have both proven extremely useful in industry to manage NVMe devices, which is why we see a need for a similar library to manage and control CXL devices. I will say that libnvme is much more mature, which is expected considering CXL is still an emerging technology itself. But the overall goal remains the same, and we still need this library to interact with and manage the CXL device. Next slide. So to better visualize this, libcxlmi will act as the Fabric Manager in this scenario. So now that we have all the parts that we need, we can actually emulate dynamically adding system RAM entirely in software. And I'll be doing this in a quick demo. But before we start the demo, I do need to go over the configuration of what we'll be emulating. We'll emulate a dynamic capacity device that is directly attached to the host VM through a PCI bus. And similar to our previous example, the device has two CCIs. The host talks to the device through its mailbox CCI, but unlike before, we're not going to have a switch here just to make this simpler. No need to complicate things. We'll also emulate an I2C bus for sideband communication, which libcxlmi will use to talk to the device through its MCTP CCI. libcxlmi will run on the host, acting as the Fabric Manager. I'm going to take a sip of water. Which is a little different from the previous example where the Fabric Manager was run on the BMC. But like I said earlier, the Fabric Manager is a logical process and can be run on either. So to make things simpler, we're not going to emulate a BMC and have libcxlmi on the BMC. We'll just clone libcxlmi on the host and use it as the FM that way instead of adding another layer of complexity. So one thing to note here is that in order to enable MCTP here, I am using a specific branch for both the kernel and QEMU because the work to enable MCTP is not upstream yet. However, it's not proprietary, it's all out there, but it's just not upstream at the moment. And another requirement here is that the kernel branch has to have dynamic capacity support, or else the host won't be able to accept the extents that the device offers to it. So if we put everything together from the previous slides, the Fabric Manager, in this case libcxlmi, uses an out-of-band link to send the FM API add command to the device. The device processes this command, records it in an event log, and triggers an interrupt to the host. The host is notified, accepts the extents that are made available to it, sends its response back to the device, and once the device actually allocates those extents for that host, the host should be able to start using that memory. So I'll be showing how to do all this using QEMU and libcxlmi. Scary. I think I need to. It's.
Move it over in the presentation.
Oh, okay.
And then move it over.
Okay, thanks. There we go. Okay. So, yeah, let me make it a little bigger. That look good? Okay. Let's move on to the demo. And I'll be using a tool created by one of our team members here at Samsung to help me do some of the environment setup steps, which can be kind of tedious and annoying. And I will talk about this tool briefly after the demo too. But first, I'm going to use the tool to start QEMU with the topology that I just showed in the previous slide. Okay, well, that didn't really show us anything, but I'm going to show that the VM actually has an emulated dynamic capacity device attached to it. So if we log in and use the CXL list command, that should show us information about the CXL devices. But in order to do that, I have to first load the CXL driver and some related utility libraries. So let me do that really quick. Okay. Okay, so now if we log into the VM and do CXL list, we see that we have one CXL device called MEM0, and it has two dynamic capacity regions, DC0 and DC1. Okay, so I'm going to log out again and just finish some remaining setup steps. One of them is I'll use the tool to run a short script to enable the MCTP endpoint that we're emulating. And another one before we start is to create a dynamic capacity region on the kernel side. And you need to do that in order to enable the kernel to actually use the dynamic capacity device. So we're going to create a DC region from our device MEM0. I'm going to log back into the VM and check how much memory that we have currently using lsmem. So it looks like we currently have 8 gigs, but shortly, hopefully, that number will increase. So I already have libcxlmi cloned and compiled on here, so I'm just going to go straight into there. And there's an example program that allows you to interactively add and release extents using the FM API. So I'm going to just quickly print the extents we have now, which is 0. And to keep things simple, I'm going to just add a single extent. And I'll make it 512 megabytes. So if we print again, we should see that the device has now allocated one extent. And I'm going to exit. When I exit, the program is going to ask if I want to create a DAX device for this region. And I do want to do that in order to actually be able to use this dynamic memory. So this first command will just create a DAX device, DAX 0.1, as we can see here. And this second command will just check that it was created correctly from region 0 using DAX-CTL list. So that all looks good. And you could stop here and just use this memory as a regular DAX device by just accessing it through the -dev directory. But I'm going to reconfigure it to be used as system RAM, just so I can show everyone with LSMEM again that we've added more system memory. So this command, DAX-CTL reconfigure device, will just change the mode to be system RAM mode. So if we use LSMEM again, we see down here that we actually have an extra 512 megabytes of system memory. And I'll just also use the NUMA CTL-H command to check how it shows up as a NUMA node. So our VM itself is node 0 with 8 cores, 8 gigs. But our CXL memory is shown as node 1 with, it's a CPU-less NUMA node. Okay, so now that we've successfully added dynamic memory, I just really want to recap what we just did in this demo. So first, we emulated a dynamic capacity device in QEMU, and we used libcxlmi to send the FM API add command to start that whole process that I went over earlier. And then we reconfigured that memory to be online as system RAM. Okay, so I'm going to go back to the slides. Yeah, so in the demo I just did, I relied pretty heavily on this tool, CXL test tool, to do a lot of the environment setup because getting it right can be pretty tricky if you're just coming into this not being really familiar with both QEMU and CXL. And you do need some extra background knowledge about these components listed below. I don't think we have enough time to get into the nitty-gritty of all of that. But my point is that the tool abstracts a lot of that away, and getting the environment set up every single time can be pretty tedious as well. So this tool can be really useful in helping you get started. And it includes a set of pre-configured topologies you can use, and also a number of scripts to help you do things such as, if you remember from the demo, I had to enable the MCTP endpoint and create a dynamic capacity region in the kernel. So this tool is super useful for that. To quickly recap some of the main points from today, we went over why CXL emulation is valuable, what you can currently emulate in QEMU, how memory is added dynamically from a dynamic capacity device through the Fabric Manager, and how to emulate that, as well as some tools and libraries that are available to help. Okay, and finally, I would like to acknowledge everybody listed here. They've done a lot of really great work to drive CXL forward, and this demo wouldn't have been possible without their contributions. So, yeah, thanks everybody for coming to listen. Questions? questions? Questions?
The mic, the other mic.
Oh, okay.
Great demo, thank you.
Oh, yeah, thank you.
Thank you. Great demo. What version of CXL is supported as of now? I'm assuming 2.0?
The official, like the latest official open spec release I've been working on out of is like CXL version 3.2. Is that your
It's
question?
nuanced.
Or-
No, it's nuanced. In QEMU, we don't have to follow a particular version. It's not the same as the hardware, because in QEMU, that connection is a PCIe MMIO emulated. So from the host perspective, it looks like CXL, but it's not really tied to 2.0, 3.0. So like say DCD is CXL 3.x feature, we've put that in QEMU, right? There's not a strict relationship as much when you're using QEMU, just because the physical connection isn't there.
Okay, thank you. And the other question I have is, so with the CXL tools, I'm assuming you can issue M2S, memory reads, memory writes for the
Yes.
commands?
Yes, you can, but again, since you don't really have that physical connection, so this is a great question, and I would say it's nuanced. We don't really look at performance testing for this. That has never been our goal. It's more functional. So the way that the master to slave request looks in this QEMU world, it's actually MMIO trapped memory accesses in QEMU currently. And we don't really mind, right? Because we don't need to worry about that level of performance detail. But there are people that are breaking that assumption and just backing it by memory on the host, and then you can get really fast accesses, but then you don't have like a software trap in between to do anything interesting too. So there's this tension there that we usually don't want to get too detailed into like physical transports. We tend to stay away from that.
Okay, so that probably answered my last question, which was, are you going to be able to look at the registers and stuff?
Of course. Oh, yeah, the registers are all there. And so one key separation I put in my mind, so all of the control plane, CXL.io requests to set up the memory, all of that behaves exactly the same. And so, yeah, all the registers needed to implement anything for like adding a multi-headed device or like querying those parameters, all of that state has to exist in QEMU. So there are registers for you to poke at and commands to send. So it's all there. That's all there.
Thank you very much.
Based on that, then her answer on support for 3.1 or 3.2 is, from an MCTP perspective, is still required for the .io stuff, and in order for you to be able to support certain things that were not in .1. Right.
Exactly. Yeah. So it's ad hoc in some way. If you think about it, we think about a feature that we think will be valuable at a given time.
Correct.
And we build all the infrastructure around it, like say all the FM API things, the MCTP based CCIs, all of that comes along with the feature, right? So we look at it as like, how could you actually do this, right? That's our goal, right? Like, what would it really look like to do this as best as we can, and then put all the software together. So that's our view.
Just to answer this other gentleman's question, some of the simulations that we were doing actually are using the memory trap that he's talking about to actually do performance testing on these types of things. So the CXL example I used earlier actually uses the exact technology that he's talking about to get the timings. But a question for you. So this DAX device that you talk about, is this part of the CXL library?
Oh, no, this is like a separate, like, Linux library that lets that kind of, it stands for Direct Access Device, and it exposes device memory as like a file under the -dev directory, and you can just access that from user space.
Okay, and then when you turn it into system RAM, you're basically mapping memory onto it?
Yeah, so basically.
Okay, and just a couple small questions on the CXL, or libcxlmi.
Yes.
Does it provide any locking capabilities so you can essentially lock memory regions?
We don't think that this library, like, it's out of the scope of this library to provide locking. It just wants to send. Oh, yeah? Sorry.
So I think you're not asking about concurrency between multiple people trying to use that library. You're asking about don't touch the CXL memory anymore, right? Of some,
Right.
yes.
Yeah. So I was going to ask the exclusivity question
Yes.
next, but
Okay.
what I'm asking about is do you have some way of saying, don't deallocate this memory?
No, well, so that's a more complex discussion, right? So that's more of a CXL spec issue. So with DCD, so DCD is very interesting in this regard, right? Because it's a dance between some consumer or somebody that wants to add memory, the device, and then the OS, right? So someone comes from the outside, this fabric manager, and wants to get memory. Then the device decides whether it has any available extents, then offers it to the host. Then the host comes back and says, okay, I actually accepted these. And so if you think about from the device perspective, you can try to remove some of these extents, but the device may ask to remove the extents. But the host can say no, but then the device can come back and say, oh, well, I'm taking it anyway, right? Because you need some like way for the device to always be in control of the state, right? We don't want to always be dependent on hosts. It's very complicated, but it's not about exclusivity, but it's about who's tracking ownership and who rightfully should control the memory.
Okay, you've answered my question, which basically you're saying that the outside device can panic your host.
Yes, of course. We could never let go of that. I think any other hard guarantee would be really terrible for the device vendor.